For question number 4, we know we need to end up with an isosceles triangle, and in order to show the triangles are isosceles, we have to show that they have a pair of congruent sides. So in this triangle ACF, which is ultimately what I'm looking for, triangle ACF. And a little hint, you know that if we're going to use the converse, we have to have started with saying that two angles are congruent. So I am going to aim for showing that angle C is congruent to angle F. And that would allow me to show that the opposite sides in that blue triangle are congruent. But angle C and angle F, I'm going to notice, also happen to be parts of these little triangles. So I am going to aim for showing that triangle CBD is congruent to triangle FGE. So I need to work on these two triangles. I already have a pair of congruent sides. In fact, I don't have these angles. I'm aiming for those angles. But I have these big segments that are congruent, and I know that what's begging to be done is take these big segments and subtract DE from both of them. So I'm going to use the subtraction property, and my second step then is going to be CD is going to be equal to EF. Again, from this statement, I'm subtracting DE from both sides. So my second step is subtraction, which gives me another pair of congruent sides, and I have to use the fact that we have perpendicular lines. So what we know about perpendicular lines is that angle BDC and also angle GEF are right angles, which of course is the definition of perpendicular. And if we have right angles, well, we know that they must be congruent. So angle BDC must be congruent to angle GEF by that very handy theorem that says all right angles are congruent. And then I have a pair of congruent angles, two pairs of congruent sides. So our triangles are congruent by side, angle, side. And then we have CPC, TC, and then the rest is done.